Hello, my name is Andrew Gary and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. I am joined by Jonathan Ajo-Franklin, editor of the special section of the December 2017 issue of The Leading Edge on geophysical applications of fiber-optic distributed sensing. Jonathan currently works as staff scientist in the Energy Geoscience Division at Lawrence Berkeley National Laboratory and served as an associate editor for geophysics from 2011 to 2016. Jonathan joins me next. So for the uninitiated, could you briefly explain geophysical distributed acoustic sensing and distributed temperature sensing?
So distributed acoustic and distributed temperature sensing are two pretty recently developed technologies. I guess DTS was developed originally in the 80s, and DAS, or distributed acoustic sensing, was really developed. I mean, it's come of its age probably in the last 5 years or so. So both technologies, they use kind of brief pulses of laser light to look at the changes in scattering along the length of a single strand of fiber optic fiber. So just to give you an idea, there are a bunch of intrinsic scattering modes which happen in fiber optics. And so when an environmental change happens around a fiber optic cable, you can actually detect that by changes in the scattering coefficients. So that could be for Rayleigh scattering, maybe there's a little bit too much in the weeds, is sensitive to changes in strain in the fiber, extensional strain, and Raman scattering is sensitive to changes in temperature. So both of these technologies use these little brief pulses of laser light. You're looking at the changes in scattering, and from that you can infer changes in strain rate for DAS or in temperature for DTS. So then you go ahead and you take what's called a time for distance transform, and you know the speed at which light travels in the fiber. So by looking at this whole train of scattering events which come back to you, you can infer what's happening at every location on the fiber. So you're basically changing this one long continuous piece of fiber into, you can imagine, 10,000 geophones, except all of them measure extensional strain rate. So it's really this local measurement of what's happening around the fiber, and it's very powerful because you're replacing a lot of point sensors with one continuous sensor where you can make measurements at every location along it. So often in situations where you're in the field, you always have to make choices with the number of sensors you can put out, and that has a lot of implications for your imaging algorithm and seismic acquisition. Here, you have sensors almost everywhere suddenly, and that's very powerful. It allows you to stack, it allows you to do types of inversion analysis which you really couldn't do otherwise. Is that a good summary? That is
a wonderful summary. You mentioned strain a few times. Could you explain to me strain and its relation to DAS?
Yeah, so DAS is measuring Rayleigh scattering, changes in Rayleigh scattering, and Rayleigh scattering changes as you start to stretch on a fiber. So it's sensitive to extensional strain in the fiber itself and to other kinds of effects where you have a wave which travels through it, which maybe causes a strain. Like you can have a P wave, which travels into a fiber and causes a stretch due to the Poisson effect. So that's changing the scattering from the laser, or from that little pulse of laser light, and from that you can infer how the fiber is being stretched. So it's actually really good. Straight fibers are really good at measuring surface waves and shear waves, a little bit less good at measuring P waves, but people are now going ahead and modifying the way these fiber optic cables are built to allow you to measure a local strain along every segment of the fiber. And that's because you're measuring changes in Rayleigh scattering as a function of time.
I wanted to get into some specifics on the papers.
Sure.
All of Santa Martina's list questions to consider for using DAS. For example, what is the instrument response, noise performance, and repeatability? What do you see as the essential questions?
Yeah, I mean, I think that those are good places to start. I mean, there's still a lot of unknowns with respect to instrument response. In theory, a lot of the different types of interrogators which are used for DAS should have response down to DC. But it looks like that there's there's fall off in the instrument response on the low end, which we're still trying to understand. And it could be due to package interactions and a host of other effects like coupling into the soil column. So while those are a good starting point, I would add in a couple of other questions which we're continuing to work on, and that includes sensitivity to different wave modes. And particularly the directionality of cables which are used in DAS, their durability in different kinds of deployment scenarios, and data handling. So, I mean, you may not know this, but when you're acquiring continuous data on tens of thousands of channels, suddenly this whole data handling becomes a much bigger issue. And this has been dealt with in the marine community when you're acquiring large 3D surveys. But a lot of people who are getting into DAS now just generally don't acquire data on quite this many channels at these rates. So, you have one interrogator can easily generate tens of terabytes a week. So, and when you have multiple of these units which are in the field recording on long arrays, you quickly run into issues with filling up local RAID systems and dealing with data handling, which can only be remedied basically by mailing hard drives at this point. So there are a lot of challenges with respect to data flow, which I would add in addition to this, basic questions about instrument response and noise performance. The wave mode question is particularly interesting. There's been some theoretical work recently on that. But because you're measuring an extensional strain, you're more sensitive to waves which are traveling in one direction versus another. So for example, surface waves which are traveling in line with the fiber, you tend to be more sensitive to those stretches than P waves which are heading orthogonal to the fiber. So there's a lot of work which is being done now on how to engineer the fibers themselves to be more sensitive to waves traveling from different directions. If you think from a geophone perspective, you're just making a vertical velocity measurement at one point. And here, because you're measuring something which is like a difference between two horizontal phones, you're measuring the stretch, you have different types of sensitivity patterns than people are used to with geophones. On the low end in the special issue, in terms of frequency response, it's a really nice paper by Becker et al., which is exploring the very, very low, like 120 second period response of DAS cables to pressure field variations. And I think that's going to be, increasingly an interesting topic. People are starting to use DAS now for measuring things which, geophysicists would usually say are quasi-static strains. So there's a great paper which is in the special issue looking at behind casing DAS to measure slow strains associated with hydraulic fracturing. So I think that's one space which it's really going to expand, is looking at these very low frequency to quasi-static effects using the same technologies.
You're kind of getting at it there. How could this technology be utilized in something like unconventional reservoirs?
Yeah. So, in unconventionals, there's the way which people have been using it to date, which is, the place where this first got adopted is in the vertical seismic profiling community, because it's generally very hard to put dense arrays of geophones in wells for long periods of time. So the first place which DAS started being used in unconventionals is probably for VSPs. And then slowly it's been adopted for a micro-earthquake recording as well. You have these directionality issues you have to overcome. But the MEQ recording on very, very long arrays is a powerful tool. Because you have so many more sensor locations, it allows you to go ahead and do a better job with hypocenter locations and potentially looking at moment mechanisms as well, moment tensors. So, sort of VSPs and MEQ was the first kind of application areas. But now, as you've seen, it's a paper by ConocoPhillips, by Bashali Roy and co-authors. It really allows you to see an example of looking at things like stress shadows from an approaching fracture tip. So that's an example of using it to look at these things which are still dynamic, but are much closer to the DC strain limit. So you can really start looking at stress field perturbations, which are induced by each stage in a hydraulic fracturing operation. So I think that's a really exciting application. And, when I sort of tell people who work on geodynamics at the larger length scales about this, they get really excited too, because there's not very many techniques which have the same sensitivity, because we're talking about nanostrain, range sensitivity, and yet you can do them inexpensively over very large length scales, particularly for unconventionals, where as laterals get longer and longer, and we're talking about more and more stages, you need a monitoring technique which is both inexpensive, but one which can scale with sufficient resolution to see each stage, but still you can instrument your entire well. And so that's a place which DAS really can shine.
And there are several papers that sort of get at this return on investment in the technology. Yeah. And, one of the things I thought was interesting in the Mativa et al. Paper, they pondered if the low-cost acquisition using DAS would be good enough in a world accustomed to getting this quality 4D data and kind of moving progressively more into 4D. So what do you think about that? And how do you understand, how could a manager understand the value of DAS, or how could a geophysicist explain that to a manager?
Yeah, well, I mean, I think that there's some domains where it's very easy to explain. So as I was referring to before, in the case of VSP, if you want to do 4D VSP on an offshore well, it barely needs explaining, to be honest. I mean, with a relatively inexpensive operation at the beginning of a well's lifespan, where you're putting in this very, very small fiber bundle behind casing, you basically can occupy and run 4D VSP in that well without having to take the well offline potentially, without having to insert anything into the well bore, to change the completion scenario. So I mean, it's for 4D VSP, I think it's almost like a give me. As long as a 4D VSP itself is something which you need to understand the reservoir, and the cost associated with using fiber for it is a lot lower than alternative scenarios like running in a locking 3-component array. I think as long as the geophysicist doing the processing can tolerate the slightly lower signal to noise of a DAS acquisition, then there's a really strong return on investment argument for DAS. I think it's kind of an evolving argument in the case of 4D surface acquisition, where we're still at a point where the fiber itself, isn't as sensitive to normally incident reflected P waves. So that's a place where fiber design and new instrumentation is really coming into play. But I think eventually there'll be a very strong return on investment argument. I think something else to remember is that even if the single channel signal to noise for a little section of DAS isn't as good as for a single geophone, the fact that you have so many more channels means that when you go to the final migrated image, you could still have as good or even better signal noise just because of channel density, even if the individual channel signal noise is worse. So you really have to think in terms of what do you get out of the migrated image. So like, let's say you had 5 locking geophones versus having 1,000 DAS units, which you're migrating. I mean, so it's that the final image domain which you have to think about. One challenge which DAS hasn't quite overcome yet is providing, true 3-component or 4-component data. And, this is because, you're basically measuring an extensional strain in the fiber itself. And you have to think about how to design a cable which has appropriately wrapped fibers to be able to look at more than one component. So that's a really interesting area of active research. There's a bunch of stuff going on at Colorado School of Mines with Paul Sava's group looking at optimal designs for cables, which haven't been realized yet. I mean, this is all on the theory side, to go ahead and allow you to record multi-component on DAS. But as of right now, there's 2 general designs which people are using. One is just using a single straight fiber, which is making a measurement of extensional strain rate. And the other is coiling a fiber around a compliant inner core, like basically a rubber core. And that allows you to do a better job of measuring P waves, which are normally incident to the cable. But it's still not a pure vector measurement, and it's certainly not 3C or 4C at this point. So in situations where you need to do shear wave imaging and you need to know exactly which vector component you're measuring, or if you need multiple components, that's something where DAS is still developing.
You joined a number of authors to study the effectiveness of a novel fracking method in a shallow well using passive DAS. What was the key question you all set out to answer, and what did you find?
Yeah, so that was a project led by Hunter Knox at Sandia, and the lead author was Stephanie James, who led all the processing efforts. So in that particular project, we were attempting to explore using a certain type of new explosives to generate more complex fracture patterns in hard rock. So the target is more on the geothermal side, where for enhanced geothermal, you need to create a fracture network to increase the thermal yield when you circulate water in a reservoir. So, typically when you induce a fracture using traditional hydraulic fracturing techniques, your fracture orientation is determined by the least horizontal stress. So you end up getting a fracture which is orthogonal to the least principal stress. And often they're what are called bi-wing fractures, and that they're relatively simple. Hopefully they'll hook into a natural fracture network, but they don't have a lot of complexity. So it makes it more difficult to either sweep a larger volume of oil and gas in the unconventional business, or to circulate enough water to get a good, to sweep out the thermal energy in the case of geothermal. So the idea behind that effort was to look at these new explosives. Now, but the problem is you come up with some new explosive method to create a fracture network, and you have to characterize it. And that's actually really complicated for explosive techniques, because, I mean, you can go and see what happens in the wellbore, but in unconventionals, what you usually use is MEQ, micro earthquakes, to help define the zone which is stimulated. With explosives, you can't do that because there's no sequential activation of small faults, which, yields the energy you record with MEQ. There's one big blast, and you can record that, but it doesn't tell you much about the spatial distribution of fractures. So in that particular project, we were trying to come at the problem from a bunch of different techniques. This paper in the leading edge was focusing on using DAS and ambient noise, but we also had active seismic and ERT and a bunch of other techniques to characterize the fracture network. Ambient noise with DAS is like a really great combination because with DAS, part of the overall paradigm is that you suddenly have sensors almost everywhere and of intermediate quality. And the question is, what can you do with it? So you end up with this great asymmetry between sources and sensors. Sources are generally, don't have many of them. They're expensive to deploy. So ambient noise allows you to go ahead and use this noise, which is just reverberating through the environment, to go ahead and simulate, active source surveys. For those who aren't familiar with ambient noise seismology, it was developed, I think, in the early noughts, and it involves doing cross correlation between ambiently data acquired without a source to synthesize these active source surveys. So if you have receivers everywhere, then suddenly there's a great advantage to being able to do processing like this to sort of simulate having sources everywhere. And then you can think about doing all kinds of things like tomography or reflection imaging. There's been a lot of work in the geophysical community on ways of leveraging this. So in that particular project, the idea was to use ambient noise and DAS to go ahead and build a map of the fractured zones. And one of the challenges with ambient noise, though, which showed up at this project and in others too, is that you're limited by the ambient noise which is in your environment. So the processed result is limited by the bandwidth of this ambient noise. So you have to think about how you're going to do the stacking, the types of noise bands which you're going to be able to use, and what wave modes in the natural environment they correspond to. So I think that project was that side of the project was pretty successful. One of the challenges, though, was that there were pretty shallow wells where this test was done. And in DAS, you're often limited with respect to the zone or the length of the fiber you can use to acquire a high quality single sensor kind of data. And that kind of zone which you're averaging strain rate over is called the gauge length. And so in that case, the gauge length was actually not that many more multiples of, it was not that much shorter than the actual depth of the wells. So, we didn't get a lot of channels because they were only 60-foot wells. So that was a little bit of a challenge to create like a really good tomographic image because it was a very small size site, and DAS is, shines when you have longer length scales. Having said that, I think the result which Stephanie was able to put together was really convincing and quite neat. And we're in the process now of comparing it to the active source data, which we acquired using an array of small piezoelectric sources. So it'll be really neat to integrate those.
Backlund et al., their paper, there was an excitement coming about the technology coming through on that paper.
Yeah.
And at one point they stated it's a paradigm change in land seismic.
Yeah.
What is this paradigm change that they are writing about?
So I think the paradigm change is really this idea of having dense semi-permanent detectors almost everywhere. Because the cost of a fiber itself is so cheap, and you don't need that many interrogators to be able to record at dense channel spacing over very long distances. It goes from this idea of having to, go out and roll out these large arrays of geophones, either wired or wireless, to having a permanent array everywhere, which you can record at high data rates. So maybe it's a little bit lower signal to noise than a traditional geophone. But when you start thinking about that, there are a lot of things you can do. There's a premium to thinking about how you build permanent sources. There's a premium for how you do noise reduction in these kinds of environments. And there's a premium for how you can use relatively short epic time-lapse data sets, right? Because if you've got these arrays everywhere, and let's say that you have an inexpensive source, and this was talked about in the Mativa paper as well, what can you do with this higher resolution of 4D data? And I'm talking about resolution in terms of time as well as space. So in Bakulin et al. In particular, they were also looking at incorporating shallow wells as part of the acquisition process, which gives you information on statics and near-surface velocity, which is really important in the context which they were writing about. But in general, I would say the paradigm shift is, what do you do when you have dense detector arrays everywhere? How does that change seismic acquisition?
As someone involved in this field, in this technology, what did you learn and what excited you about going through these papers and being involved in this section?
Yeah, well, I mean, so there was a combination of like new technology examples and sort of really good case studies where people were kind of trying to push the technology in different directions. So I really liked the Becker paper I liked all the papers, but the Becker paper I found particularly interesting because we're doing some work on, detecting like local and regional earthquakes using DAS. And in the Becker paper, they showed for the first time what the response function looked like at very low frequencies. Most of the seismologists who work in SEG, you're thinking, from half a hertz to 100 hertz. That's the kind of frequency band they live in. So there were not very many examples of looking on the very, low end of the frequency spectrum. And he actually did a really nice job, building a little kind of signal to noise plot for different low frequency measurements using a nicely designed little water tank, basically, which changed pressure. It oscillated it at very low frequencies. So it sort of gave the first hint of that response function on the low end. And it's interesting that response drops off as a function of frequency as you go towards DC, but not as quickly as a lot of people thought. The other paper which I really like too is Bashali Roy's paper, this Conoco paper, which really again showed this idea of doing dynamic strain measurements on DAS. I've done some measurements, strain measurements using fiber optics before, using related technology called distributed strain sensing, which uses Brillouin scattering. But I'd never really seen a great example of doing dynamic strain using a DAS unit. So it's just a very compelling paper. It's also the cover, if in case you looked at the actual physical paper cover. But once you can look at things like stress shadows and changes in stress state during unconventional production and stimulation, you can start thinking about how do you optimize the stages which you run in unconventional wells based on the stress state and how you perturb it. So it really kind of suggests that there's a lot of opportunities with using stress state monitoring using DAS to kind of carefully design and optimize the way which you change permeability in the subsurface. So having strain everywhere too was kind of a really neat thing. So I think that both the Wu paper and the Becker paper, which are exploring the low end of DAS response, were ones which I particularly excited me.
Would you recommend, maybe there's a geophysicist listening to this or seeing this technology that maybe their first thought isn't this is applicable to my work and my job? Do you think there's someone, a particular branch of geophysics that would find this interesting that maybe at first flush wouldn't draw the connection between their work?
Yeah, it's really, I think the problem is more the opposite. There are not very many sort of zones where it's not applicable. And that's the exciting part about it. When I give talks on DAS at very academic places and very applied places, everybody's, excited by the technology and the opportunities. So I think that everybody from earthquake seismologists all the way up to people working on ultrasonics and sonar, can find a niche, which they can apply DAS and these other types of distributed sensing modalities. It's harder to find places where it's not applicable.
What do you hope readers of the special section take away?
I hope they take away the wide range of applications which DAS and we have one DTS paper can be applied to in geophysics, and I hope they kind of appreciate that it's a technology which is getting closer and closer to the way they traditionally acquire data. That it's something which because of its the current and improving price point, it's very competitive, if not exceeding traditional geophone acquisition in a lot of different contexts. I hope they see that it can be applied not only to seismic, but to much lower frequency measurements as well, looking at things like dynamic strain. And it can be applied for both cases where you have sources, like traditional Vibra-size studies, and to situations where you're just looking at environmental noise, like ambient noise seismology. And I hope they appreciate that, it's a great field to get involved with a lot of opportunities.
And just one more question for you. What are you most excited about in this field to discover or to see the possibilities of it existing out there?
Yeah, so the part of the future which I'm involved with, and there was one paper which discusses this in the special issue, is the idea of using existing telecom fiber optic networks to record seismic data. So as you may know, fiber is pervasive in our natural environment. There's a lot of it which has been installed over the years for fiber optic communication. And, we're really interested in going ahead and using that as kind of a massive seismic sensing array. Myself, more for near-surface ambient noise studies, and then also for traditional seismology applications. But you can think about a lot of different applications you can use that network for. And the most expensive part of installing fiber networks on the surface is the actual trenching or drilling process to get the fiber in the ground in the first place. And so with telecom fiber, it's already been done for you. All those permits have already been made, and there are many, many kilometers, tens of thousands of kilometers in the United States, which are installed already. So we're working hard on that. There's a paper by Eileen Martin and Biondo Biondi in the special issue, which explores that kind of recording on the telecommunications network, which is at Stanford University. And we're looking at it on the much larger scale on a section across the Sacramento Basin to do things like groundwater monitoring and also detect local and teleseismic earthquakes. So that's actually something I'm really excited about, is using the sensors which are everywhere, which you don't even have to pay to install them. You just have to find the place where you can hook into the network and get permission. And suddenly you've got these 10,000 channel arrays.
Any other final thoughts to share with our listeners or the readers?
One thing about DAS too, which, I wanted to mention, is that the ideas behind it are actually not that new. They're from the 80s, and a lot of Navy patents in the 80s for listening for submarines using these types of methods. But really, because of the advances in the interrogators and the photonics, the laser sources and detectors, in the way in which the special purpose cables are designed and the processing, it's really only very recently that this has become a way which we can do things, like maybe the last 5 years. So for listeners who are excited about it, this is their chance to get in early and, and learn about the technique as it's still expanding. So, even though we've got this history, it's really a pretty young field. So, it's your chances now.
At seg.org/podcast, you will find the show notes and links to the December TLE. Subscribers can read the full articles in the SEG digital library, and for those currently not subscribed, abstracts for each of the leading edge papers are always free. To learn more about becoming a member or subscribing to the leading edge, visit seg.org/membership. If you enjoy the show, please leave us a 5-star review on iTunes. Your review helps others find the show. Subscribe to Seismic Sound Off on the podcast app of your choice to receive the latest episodes first. Seismic Sound Off is sponsored by the SEG Wiki, home to hundreds of biographies of key geoscientists, geophysical tutorials, and core content from the science of applied geophysics. Visit wiki.seg.org to learn how you can grow the world's first online geophysics encyclopedia. Original music by Zach Bridges. This episode was produced by Isaac Farley and hosted, edited, and produced by me, Andrew Gary. Thank you for listening. This is Seismic Sound Off, signaling off.